This video is all about color, with specific applications to Photoshop. I'm your professor, Marty Pfeiffer. Believe it or not, any color can be produced by combining just 3 base colors. The 2 systems for doing this are called RGB and CMYK. Photoshop offers several methods for storing and working with color information. This will involve color modes and bit depth. In addition, we'll discover how Gamut and Color Profiles work. You'll be able to produce images with consistent-looking color on a laptop screen or a printed page when you understand these concepts. So where does color come from? Color can be created directly from a light source or indirectly using pigments, such as ink or toner. These are the additive color model and the subtractive color model, respectively. In the additive color model, color is produced by combining red, green, and blue light. This is shortened to RGB. If you remember painting class in elementary school, you may be wondering why it's green instead of yellow. Aren't those the primary colors? Well, it turns out you're thinking of the subtractive color model. In the subtractive color model, cyan, magenta, yellow, and often black pigments are layered on a surface. This is shortened to CMYK. The K stands for the word key. In the printing world, a key color is used to make sure the other colors are correctly aligned on the page. It is handy to do that with the darkest color. In the additive color model, the colors of light mix in non-intuitive ways. Bafflingly, when red and green are combined in equal amounts, they produce yellow. That's just how light works. As you see in the center, all 3 colors combine to make white. White light is essentially all the colors in equal intensities. This graphic was produced in Photoshop by layering 3 different colored circles on top of each other and setting their blending mode to screen. Blending modes make layers with overlapping areas interact in various ways, rather than just the top layer hiding the overlapping regions of the layers below. We'll explore blending modes throughout the course, as they are a key component of using Photoshop. Mixing colors in the subtractive color model works as we expect. Look at the bottom. That's a shade of blue, technically called cyan, mixed with yellow to make green. When you paint, this is how the colors can be combined to create other colors. And if you mix all 3 colors, you get a dark gray. Theoretically, you can make any color just from these 3. But practically, we add white and black paint to make different shades easier to achieve. This image was created using the multiply blend mode. It's surprisingly hard to produce a good black from colored ink on paper. So we use actual black ink to do that. Along with the white color of the paper, we can approximate any color using just cyan, magenta, yellow, and black ink. In addition to RGB and CMYK, Photoshop also supports color in several other ways. The most basic is grayscale, which is just all the shades from white to black. Internally, Photoshop uses a color mode called LAB, which is pronounced L-A-B and not lab. Whereas the other color modes document how the color is created, either by varying the intensities of light for RGB or adjusting the amount of pigments for CMYK, LAB attempts to describe what the color looks like. It breaks a color into 3 attributes: L for lightness, A for the red to green color range, and B for the blue to yellow color range. This forms a 3-dimensional axis, pictured here. Older 8-bit computers lacked sufficient memory to handle images with large numbers of color, so they used a hack. They produced an indexed color table, where each element of the table contained the recipe for the levels of red, green, and blue required to create a specific color. Each pixel of the image would be defined by its X and Y coordinates and an index color value. So it saved on memory used and file size. However, as a side effect, it limited the number of different colors that could be displayed. We used index color in GIF and PNG files. Multi-channel is for specialized printing purposes. As it does not support layers, you will not use it in your general workflow. It is a mode you use at the end of a project to produce a specific printed result. Duotones are when you use 2, 3, or 4 colors to represent different ranges of luminosity. So dark areas of the image could be just represented with the black ink, but more mid-tone regions could be made of a mix of black and brown ink. And then the lightest areas could be just shades of brown ink. And of course, that's a standard duotone. You can get more creative if you go outside of strictly representational art. Most of your work in Photoshop will be done in 8 bits. Wait a second, 8-bit? That sounds like those old computers from the 80s. When we say 8-bit, we mean 8 bits per channel. Essentially, an image uses 8 bits, or 256 shades for each channel of red, green, and blue. That sounds limiting, but the math works out to allow you to produce 16.7 million different colors. In some specialized cases, you'll need to use a 16-bit depth. This will produce 281 trillion colors. And then we have something called 32-bit. Think of 32-bit as basically 16-bit, but with f-stops added on top. This provides you with more flexibility when working with high dynamic range photography. Like I said, 80s computers were limited. They usually couldn't even produce the 256 theoretically available in 8 bits. Since they used index color with low bit depths, this resulted in color banding for any photographic images. Let's take a quick look, starting at 1 bit. Here's a scene made of just 2 colors. Each pixel is either dark or a light color. It's kind of hard to tell what this is. 2 bits will give us access to 4 colors, and we can start to make out a clearer picture. However, it's unclear whether the background is water or sky. 3 bits. Okay. Yeah, that's definitely the sky. We can also see some slight definition in the rocks. There's some texture in the front, but the sky, that's not how the sky normally looks. There's some definite banding between the different colors of the sky. We get more defined foliage when we switch to 4 bits. We're starting to see some definition in the sky, which looks promising. But 5 bits still has that banding we don't want. The banding starts to get taken care of when we go to 6 bits. At 7 bits, we're almost there, but we're about to reach the limit of old-timey computers. So here's 8 bits, and darn it, we still have that banding in the sky. If only there were a way we could fix this. Boom! Here is 24 bits, or 8 bits for each of the 3 channels, if you want to be technically correct, which of course is the best kind of correct. We now have a bright, vibrant image. The sky looks wonderful, and we can see the foliage in beautiful detail. Better processors and cheaper memory led to significant improvement in how computers could process images. Gamut is basically us throwing up our hands and saying, color systems have their limits. This horseshoe-shaped rainbow indicates the colors that the human eye can perceive. Different animals will generally perceive different wavelengths of light as colors. Some are more limited, and others can see a spectrum beyond what we can. The illustration doesn't represent the saturation or lightness of these colors, only their hue. It's an abstraction of the total colors, not the actual total spectrum of colors themselves. When producing printed material, the most cost-effective way to produce photographic color is with 4 inks: cyan, magenta, yellow, and black. You remember the CMYK color mode from a few minutes ago, don't you? That's this one. This color profile will only allow colors that can actually be printed in a normal CMYK process. Although you don't generally work in this color profile, it's important to keep it in mind when producing printed material. You want to make sure that the RGB color space you work in will be able to display all the colors contained in this crooked pentagram. This is the sRGB color profile. It's the most common profile for images intended for the web, as it represents what the average computer monitor can display. It's a good general-purpose color profile. However, it won't be able to display certain blue and green colors that can be achieved using CMYK printing. Adobe RGB is a larger color profile, and importantly for graphic designers, it includes all the colors in the CMYK color profile. In a color-managed workflow, Adobe RGB provides the most flexibility. As long as you do a reality check on your colors, either by printing a sample or previewing using the method we'll learn in a few minutes, you can work in this profile. This will save you from having to manually convert your colors to CMYK before printing. If you're a professional photographer, you might want to shoot in ProPhoto RGB, which is very close to the entire visible color spectrum. In fact, it even extends beyond those. The critical thing to remember about all these color profiles is that they're all using the same number of bits to represent different ranges for each color channel. So, a bigger profile isn't necessarily better. Remember the banding in the sky from the bit depth demonstration a few minutes ago? If you're using a ProPhoto profile for an image that will be printed, you'll wind up using only 5 or 6 of those bits rather than 8. Fewer bits equals more banding. By the way, Photoshop uses the LAB color space to convert from one color space to another. This provides the best fidelity since the LAB is a theoretical representation of color. So here's where it comes down to brass tacks. How can we ensure that our color images print with the same color we see on screen? This is a very vibrant image that looks great on screen. But will it print? The technique I'm going to show you requires your image to have a color profile applied. You can tell an image is missing a color profile by looking at the tab above the image. In addition to the file name, Photoshop also lists the current magnification percentage, the selected layer name, color mode, and total bits per channel. If you don't have a color profile, it will display a hashtag after the total bits per channel. You can assign a color profile by going to Edit, Assign Profile. When in doubt, sRGB is a good choice for images that lack a specified color profile. Go to View, Proof Setup, and select Working CMYK to check how your graphic will print. Now you're set to proof your colors. Once again, go to View and this time select Proof Colors. When your image has a color profile assigned, it will show a good representation of how your image should print. If it isn't apparent which colors are affected, you can select View Gamut Warning. It turns out all of those vibrant colors turn to gray. Much of this image can't be accurately represented on the printed page. You can even test what colorblind people will see by going to View, Proof Setup, and then choosing one of the 2 color blindness options there. Here's a review of all those options from the View menu. It's good to keep in mind that these view options are toggles, so you can turn them off by simply selecting them from the menu again. Once you have identified where your colors won't print correctly, you can take steps to adjust those colors to ones that you prefer. The goal is to create an image that looks good both on screen and on the printed page. Good luck!